Okay, hello everyone. Welcome back to Recitation 2 of CMPS 257. In case you're just joining in, I'm gonna send it again in the chat. This first link is if you wanna draw something, draw an Automata, DFA. The other link is if you wanna submit something. So during the recitation, if ever I say, hey, let's solve this together, or if you ever want to solve something, you can submit using that link. Like we can check it live during the recitation, so we can go over hopefully if your answer is correct, or maybe more usefully, if you did something wrong, we can try to fix it. Now, for today, we're gonna be focusing on NFAs, so non-deterministic finite automata. But before that, we do have a couple of ideas we want to go through. Starting with maybe what we did last week. So remember we said this idea of we want to have questions always at the back of our mind while we're solving. So one of these questions is, hey, what states do I have? Which one is the start state? Which one is the accepting state? Is the empty string accepted, etc. So like a list, like a checkbox you go through as you're solving, is everything okay? Another idea we talked about is the draft state, which essentially it's just a state. If you enter it, you're never coming out. Now, is it an accepting state? Is it a rejecting state? It's up to the situation. Usually it's going to be rejecting. And we ended it at abstraction. We didn't completely finish the idea, so we're going to go over it again now. So abstraction. Again, the idea of abstraction is we want to use black boxes, which is like when you use a function encoding that you might not have written yourself, or maybe you've written and you put it in a library. So like you're using a block box, you don't care what's inside, all you care about is the functionality, which in this case is this DFA. So given a DFA that accepts the language L1 such that the strings that it accepts has no B's and a multiple of 5. Now remember, languages in our sense, they're going to be made of a family of strings. So in this case, we're saying L1 accepts the strings that have no B's in them and they are multiple of 5 A's. So the way we see it is just, again, some box. I don't care what's inside. All I know is if I feed it a string W, it's going to say yes if it has no B's and a multiple of 5 A's. It's going to then say no other one. And it doesn't literally have to be W. So it's just an arbitrary letter or symbol. Like I could have put it as an X, a Y, Z, K, whatever you want. It's just a symbol. And if you see this W in like when we define other languages, it doesn't have to be the same W. It could be, but it doesn't have to be. It's just some random letter. So we have this as given. And we're asked, give a DFAB that accepts the language L2 such that the following. So L2 is actually going to be the concatenation of two strings. The first one, W, which doesn't have to be the same as before, it has a multiple of 5 B's and an A's. So it's different. It's kind of the opposite, but not exactly. And U belongs to L1, which is the language we defined before. So L2 is actually the following. It's the concatenation of two things. First, this red string, which they haven't defined, but we can define it as like a mini language, L prime, which again, it's the strings that have multiple of 5 B's and A's, concatenated with L1. What's L1? No B's and a multiple of 5. So L2 is simply, you get this one string from here, another string from here, and you join them together. And we usually use this O symbol to mean concatenation. So if you really look at it, what is this? L prime is saying multiple of 5 B's and no A's. So essentially it's just saying I want some multiple 5K of B. K is just some like positive integer. And after that, we want U, L1, which is simply no B's, multiple of 5 A's. So some 5 of A's. Doesn't have to be the same multiple, which is why we use different letters. That's all it really is. Multiple of 5b's, 5 followed by multiple of 5b's. And we could draw this ourselves. We could do it from scratch ourselves, but they're saying no. For this part, we want to use M1. We want to use the machine. So I'll draw it here. We'll call it M1. We did that before, so let's just call it M1. So a DFA M1, a language outing. It's going to take a string. So at some point, we want to feed it something here. So now let's actually work on this other one. So 5KB, etc. How could we do this part? Any suggestion? Like maybe how many states I could have? Or what I could name them, something useful. So I could start off with like a 0B. Like so far, I don't have any B's yet. And like when it comes to multiples, if they tell me multiple 5, multiple 3, multiple, etc., a good way to do that is just simply count how many you have. Like right now, we want to count the number of in the like we're cheating in the way we're counting because we don't really have a variable. So what we're doing is using states. So if I read a B here, okay, now I have one B. If I read another one, two B's. Another one, three. I don't know why it shows multiple 5. And finally, here, if I read one more B, where should I go to? Anybody tell me? So this is my 5th B.
I think back to 0, right?
Yeah. I could have made a new state called 5B, and that would have been fine. It would have worked out. But why do that when I can simply go back, as Rushdie mentioned, I go back to the start. Because 0B is like 5B is like 10B. It's a multiple of 5 if we assume 0 could be one of the multiples. Okay. Now, if I'm just working on the red part, this would be my accepting state because I care about multiple of 5Bs. And where do I go when I read an A on all these other states?
Lab state.
Yeah. So for every one of these other ones, let me actually not do that. It's not really a good idea to just join them together like that. So for every one of the other ones here, they're all going to go to the trap state because, okay, you're counting how many B's you have, and it turns out it wasn't multiple of 5. So we go to the trap state and we're stuck there for. And again, if we were only solving L1, this would almost be the machine. I still have to figure out where does this A go to. If it was just L1, it would have went to, oh, sorry, if it was just L prime, it would have also went to the prime because I don't want this. But since I'm actually building L2, where does this one go to? So if at 0B, like the multiple of 5B's, I read an A, where should I go to? And I'll kind of draw here what we have. So at M1, okay, you have your start state. You might have some other states. You might have some accepting states, maybe one or more. So I'm telling you, we're building like Lego pieces together. We want to click them together. So here, the missing puzzle, where should this part go into M1? Because the red part, we've counted multiple of 5B's and no A's, which is this W. Now a machine M1 is going to take care of the U. Machine M1 is going to take care of the blue part, which is multiple of 5B's. Can
We
anybody
should go to 1A.
Aha. So it has, of course, it has to go to something. Now, if I had said it should go to the start state, that wouldn't have been really correct because it would have been as if I ate one A. But I'm reading an A. So exactly, there's going to be some state here that's reading 1A. That goes from the start state to there. And simply, I want to go inside. Let me just keep it as a blue because now we're not. So I simply go there. And this is completely okay. Why? Because if you remember the rules of the DFA, for any state, you can have as many incoming transitions as you want. I can have as many A's coming in, as many B's coming in, etc. Not the same for the outgoing, but for here, it's okay. So that's fine. And yeah, technically we're done. This is what they wanted. You're not, if there's a part you didn't get. So we built this bigger machine for
Sorry,
Mhm.
Professor, but the part when you go from 0B, when it extends to A and it goes to this machine M1, I'm not entirely sure what that means. Can you like re-explain that quickly?
Sure. Okay, so remember, what are we doing? We're building a machine, let's call it, for example, M2 for L2. We already have a machine called M1 for L1, which is this blue part. All that's really left is to do the machine, which is for the red part, L prime, which is just multiple of 5Bs and no As. And we're doing that. We did it with the red. Once you read an A here from the 0B, that means I have a multiple of 5B, which is great. And I read an A. So now I have to check for the multiple of 5As. But I'm not going to do that myself. I want to use abstraction. I want to use this other machine that does it for me, which is here. So I have to plug it in somewhere. Because what is M2? M2 is everything we did. All this, like the red part and the blue part together, they make this bigger machine. But how can I plug it in? Now, this is a drawing part. You could describe it in words as well. Like if I have an if I have an outgoing A transition from the state, it should enter the state in M1 where I've read 1A so far. Okay, like it's you're kicking off. M1 now will take care of the multiple of 5As. All you did was you gave it the first A. And then it will work on its own. Is it clear now?
Yes, yes,
Great.
it's clear.
But, okay. And again, you could imagine, I don't want to like overdraw over scratch here, but you could imagine this whole thing that we built is our M2. It's like a big machine that has things inside. And actually the cool thing, the red part that we or the whole thing, M2 that we did, now you could abstract even that. So now, for example, you could give M2 a string and it'll check for you if it has a multiple of 5Bs followed by a multiple of 5As. And you don't have to like do that every time. You can simply use that abstract machine to solve even bigger problems. Sort of like if you do a separate function or if you use an outside function to build something bigger here. Great. But now this next part, what does it say? Give a DFA-C that accepts the language L3. Now the description of the language is the same thing. W is still 5Bs and no As, multiple of 5. And U is still an L. The difference is we flip the concatenation, which gives us a completely new language. So L3 is now actually going to be L1 concatenated with L prime. And remember, L prime is just this red part. Just multiple of 5Bs and no As. Okay. So question. Can we now do the same thing, but like in the opposite? So now first I'll put the machine on one. Okay, so start, some states, and the accepting. It could be just one accepting, but like since we're talking in a general sense, I put multiple accepting to mean we might have more than one. Okay, and on the right side, I won't draw it again, but essentially we count the multiple of 5Bs. So like 0B, 1B, etc. How can I now put these two together? Any suggestion? How could we do that? So like maybe the first question we want to answer is, from where should the outgoing transition be from M1? Where do you think? Like where does M1 satisfy what we want?
I would think it would be like the reverse where M1 goes into the red diagram as opposed to the last one where it's the opposite. The red goes into the M1.
What do you mean?
Like once you're done with M1, then you put an arrow that goes then into
Exactly.
0B.
What does it mean I'm done with M1? Like what did it mean that we were done here with the red part?
When you reach an accept state, right?
So same thing here. What does it mean that I'm done with M1? It means, okay, from the accepting state, I now have to make a transition from all the accepting states.
Yeah.
I have to make a transition here. You could argue maybe to the start or maybe to 1B like we did before. We can talk about that. But question, is this legal? Yes, Ronnie, exactly. Zero. So from 0A, which is kind of like my accept. But is this okay? Are we breaking a rule here? I think we are. Because unlike before the 1A here, we're adding an incoming state to it. But here, if you think about it, like if you actually draw this 0A, it already has some outgoing A that's going back inside the machine and some outgoing B that's going back inside of it. Why? Because M1 is a complete DFA. So every state is going to have, in this case, exactly two transitions, A and B coming. What we're asking for here is, okay, if you read a B, for example, you should come here. But this isn't okay, right? It's not allowed for me to add another B here. It's no longer a DF. And I can't use epsilon either because that's also something that has to do with NFAs, not DFAs. So both of these wrong. So what does that really tell us? It doesn't work in this scenario. Okay. So if I want to use it doing abstraction, I can't do it. The language itself at L3, of course, I can do it from scratch. Like write maybe 10 or 12 states, I can write it. But actually using this abstraction idea, it doesn't. So this part is not. If anybody didn't get why not, no. But once we actually explain NFAs, you can see yourself how maybe this could have been solved in an NFA. Omar, M1 actually doesn't know the language prime. Is it the reason? Doesn't know L prime? No, that's not the problem. Like L prime is being taken care of here. So what we wrote in the red here and before, this is what takes care of L prime. The problem is I can't go from M1 to here. Because if I want to do that, it means I have to have a transition coming out of an accept state. But I already have the maximum amount coming out. And like the only amount actually in DFAs, I already have it. If I want to add an extra one, I'm breaking the rules. It's no longer a DFA. So remember the rules that we mentioned last time. You can have as many transitions coming out, and as many coming in, like I drew here, as many coming in. But coming out, it has to be exactly two. Since M1 is already a DFA, it means I already have exactly two coming out. Okay. If there are no more questions, this is basically abstraction. You have some box you want to use to build a bigger box or a bigger machine. And it might not always work. So with practice, hopefully it will come. Now let's talk about this new idea, which is what is the algorithm? So it's a new idea or a new way of thinking. Some problems have a trick to solve them, or there's an algorithm to solve them. Like Just like when you're writing maybe a function for Java, for C++, whatever, there's a sequence, there's a series of steps that you do to solve a certain issue. It could be the case also here. So if we go with the problem, give a DFA that accepts positive integers divisible by 3. What could we do here? First of all, what's my output? Positive integers. So it's the strings that are made up from these symbols, which are just the digits of the alphabet, of the decimal numbers from 0 to 9. Okay, great. This is my alphabet. So for example, one string that I could get would be, say, 23, 7, 4. This could be a string that I get. Okay. Does anybody know a trick on how I could know if a number is divisible by 3 or not? Okay, so Ronnie's saying something actually really good. Ronnie's saying that actually if you modulo this by 3 and the answer you get is 0, that means it's divisible by 3. So what Ronnie's actually telling us is that the number of states is going to be 3. Why? Well, there are 3 possibilities. You either have a remainder 0, or you have a remainder 1, or you have a remainder 2. These are only the 3 possibilities. So Ron is actually answering the question, which is, hey, how many states I have, or what are my states, which is great. But in terms of tricks, which I think Andre is answering, add the numbers together. If it's multiple of 3, I think what we meant is, then it's divisible by 3. Exactly. So in case you don't know this trick, essentially what it is, you see this number. I could do what Ronnie said. But in DFAs, I can't do this. I can't say, hey, you number, are you divisible by 3? Instead, this trick is saying, if you add the numbers together, and if the addition is divisible by 3, then the number is also divisible by 3. So there are 2 ways. You can either just say modulo for the whole thing, or you can say modulo for the addition. If you weren't familiar with that before, that's okay. Let's just assume this is a fact now. So I add the digits, and if the sum is divisible by 3, then it is divisible by 3. Now, this isn't the complete algorithm just yet. Why? Because if my number is really big, and like I sum the digits over, I might just end up with another really big number. It'll be smaller, but it's still going to be big. So what we need is, yes, it's already going to be sort of like a loop, okay? But what we're going to be doing is, instead of waiting until like the end of the loop to check for the divisible by 3, we'll do it at every step. So like, hey, so far you have 2, is 2, you'll get the remainder after you divide 2 by 3. Then you add 3 to that, you'll do the remainder and check the remainder after you divide by 3. Then the answer to that, you'll do it for 7. So again, instead of waiting until the end when you sum everything, we're going to be doing it at every step. Because we can't wait with DFAs until the end. I don't have memory. I have to do it at the very end. And I'll still get the same correct answer. And I'm going to explain why this works, the addition. But for now, let's just see the algorithm in action. So step 1, I'm at remainder 0. If I read a 0, where should I go to? So far, my remainder is 0. Where do I go to when I read the another 0? It's like I'm saying, hey, so far you have 0. You're adding another 0. It's still 0. So exactly as Andre's saying, we loop back to our self. Are there other numbers that will make me loop back to myself for R0? Remember, like whatever you add, quickly you're dividing it again by 3. So I'm just saying the multiples of 3. Yeah, if you think about it, take 0, 3, 6, and 9. All of them I'll loop back to myself. Why? Okay, my remainder is 0. I read a 6, for example. So far I have 6. Well, the remainder of division of that is just 0. So I stay where I am, etc. Same thing for 3, for 9. All right, what about the other numbers? Ron is saying 147, where do those stay? So 147, y to r1, 0 plus 1, obviously, I'm r1. 0 plus 4, after division, it's still gonna be 1. Same thing for 4 and same for 7. And okay, we still have we still have a few numbers, which are 2, 8, and I think 5. So 285, if you add 0 to that and you check the remainder, you go there. So 2, 5, and 8. Andre, we complete the rest of the table the exact same, 100%. Now, might as well do that. Let's complete it. But I'll do this first. I'll do this so we can make things just a bit easier. So I'll just call this set A, this set B, and this set Y. C. The reason I'm doing this is because you'll notice these like sets will always take me to the same, like they're gonna become like one package. So I'm just doing this so it becomes easier to write. So for example, R1, where do I loop back with myself? So I have a remainder 1. What can I add where after I did multiple 3, it's still gonna be 1. Under saying 0, so 0 takes me back to 1. Exactly, because if you add 0, if you add 3, if you add 6, if you add 9 to 1, when we're talking about in the modulo sense, it's as if you're adding 0. Like you're adding something that once you do the modulo, it's gonna go away. So I get some, so all of this, when you modulo 3, it's still gonna give you 1. So I'll loop back myself on the set A, which again is just 0, 3, 6, 9. What takes me to R0? Well, so from here, what takes me to here? So it's like you need to add 2 to 1 exactly, which is the C set. So 2 or 5, or when you model it, you get it back there. Now, what takes me back to R2? Since we did this trick of naming the sets, or that we're left with is B. But if you dive into B, it's like you're adding 1 to 1, which is left with 3. Now again, I'm doing this set idea because I already knew that they're going to be the same for every state. Don't just assume that it will always be. So like doing the set idea so we don't accidentally get a wrong answer for some. But now R2 loops back on itself on A, like the remainder 0. I go back to R1 for, what do you think? For which set? Like when I add, I think 2, right? When we want to add 2, exactly, Andre. So it's C. And finally, we go to R0 when we're left. Oh no, we're done actually. Oh no, my bad. I think for B. So B is 1. Yeah, 147. Great. So this is how we solve this exercise with this trick of we add. And again, we modified it by whenever we add something, right away we do the model. But now, thank you actually, Andre. Before now, not only what is my start state, what is my accepting state? So my accepting state is obviously going to be R0. But what is my accepting state? Also R0, because like before you even start adding, like before you start adding the first number, it's like you have you can imagine like your number starts with zeros. Yes, so it's like you already have it. So this is your number. Good question. Now we get to the next part, which is this. Same question, but now instead of decimal numbers, we want to do it for binary numbers. So like your alphabet is just 0 and 1. If you're not familiar with binary, I'll just remind you a bit, or if you forgot them. So like if I want to count, this is 0, 1, 2, 3, 4, etc. Now my question, will this same trick work here? So will the same trick of just adding the numbers also work? Andre's saying no. Why? So if we actually focus on one of these, like if I focus on this one, which is the 3, and I try to do the same trick, which is like, hey, 1 plus 1, I'm getting 2. But I just mentioned like 1, 1 in binary, it's 3. So this should actually be divisible by 3, but I'm getting 2 here. So why does it not work the trick? Well, we're going to have to understand the trick a bit more. So if I go back here and I try to find my cursor, okay, what is the trick really doing? So if I have some number 1, 2, 3, essentially what's happening, and like so far I'm starting to read the first one. Let's say I read the first number and I have 1. When I want to read the second number, the trick says 1 plus 2. But what's really happening is like you're multiplying 1 by 10, then you add to that 2. So you actually get 12. Which makes sense, right? Because now if I want to add 3, it's like I'm multiplying the 12 by 10, and then I add 3. So I get the 123. Like this is the origin. But how does this relate to the trick? Well, I'm not going to dive too much into it, but essentially 10 modulo 3 is just 1. So when you actually say, okay, I have 1, and I'm getting a 10 plus 2, in the modulo sense of the word, 10 is as if you're, when you say 1 times 10 in modulo 3, it's as if you're multiplying by 1. So there's no need to say 1 times 10 plus 2. You could have just said right away 1 plus 2. That's where the trick comes from. And like if we keep going with this, so what you really have is the following. You have 1 times 100 plus 2 times 10 plus 3. All of this modulo 3 is equivalent to just saying 1 plus 2 plus 3. Because obviously, if 10 modulo 3 is 1, 100 modulo 3 is also 1. So all of this is because Andre, can you multiply 2 power n and have the same effect? Exactly. Now, instead of doing the trick, we're still going to be doing the same thing, but now we're going to actually rely on the reason why we said 1 plus 2, which is the following. It's 1 times 10 plus 2, all of it modulo 3. So if we do the same thing on the other side, which is here. So now it's actually going to, if I have 1, so I'm doing it for the 3, this for 1, 1. If I have 1, and I get another 1, I multiply it by 2. So this is 2 in binary. And then I add 1, which is technically, in binary, it's 2, but in decimal, it's 3. So we're still using the same algorithm. Simply, it's, okay, currently I have 1 as a remainder. I multiply it by my base, which is 2, and then I add 1. So I get 3. So right now, my remainder is 3, and if we're talking in the modulo sense, it's as if it's equivalent to 0. Let's try to do it. We're going to do this. So we're going to do the same thing, but now with this side. So I'll still say, like that, it's still the same exact question and algorithm. Remainder 0, remainder 1, remainder 2. Now actually it might be a bit easier since my alphabet is only 0 and 1. We have way less transitions. Okay, I'm at remainder 0 and I get a 0. Where do I go to? So I'm saying like I have 0, multiplying it by 10, or sorry, by 2, and then I add 0, it's still 0, exactly 1 in 100. I just go back to my sum. What about 1? Okay, I currently have 0 as a remainder. Multiply that by my base, 2, then add 1, and that's 1, okay? So far, not really confusing because this is just, you have 0. Now for R1, it might become interesting. I currently have 1 and I get a 0. Where should I go to when I read a 0? Do I loop back on myself as well? I have a 1 and wait, 0. Think about it. I have a 1. So I multiply that by my base, and now I get a 0. What is this number? It's 2 in binary, right? Multiply by the base, that's 0. So it's actually 2. If you want to think about it in a simple way, imagine you had 1 in binary, and now you're concatenating to it 0. This is 2. So reading 0 actually takes me back to 1, R0. If it's confusing, focus with me now on the other one. I'm at 1. Oh, my bad. I said I get a remainder of 2, so I should go to R2. So okay, now I read a 1. So focus with me. I already have as remainder 1. Multiply that by my base, and I get a 1. So it's as if I have now 3 in binary, which is remainder 0 because it's 3, it's divisible by 3. So we go back here, which is really interesting when you think about it. Let's keep going. I only have 2 left, the remainder 2. And literally, I only have 2 transitions left. So what is 2 saying? So if we really want to understand it, let's just try it for 2. What is 2 saying? I have a remainder 2. If I get a 0, where should I go to? So like I multiply this by 10, and I add a 1. And I said 10, but like I mean my base, which is actually 2. Andre saying R1, let's see if that's correct. So 2 times 2 is going to give me 4 plus 1. It's this, which is 5. Which is when you modulus this by 3. So let me actually first write it in decimal, so it's better to understand. So this is like 5 in decimal. Modulo this by 3, because we're always doing that for every step. So exactly, Andre, we actually loop ourselves for that. I said 1, right? Okay. And again, like we could do our own trick for the binary part, yes? Like just stick to it what you want. So right now I have R2, which is 2. I read a 0, just stick a 0 to it, concatenate that. This is the number that you now get, which is 4. You remainder that by 3, you're left with 1. So you go back to 4. So this is how we do this. You didn't, if there's a part you didn't get, let me know. the thing we're focusing on is like the algorithm, the way of doing something. And in this case, really understanding why this trick works for the divisible by 3. Mhm. Now, you might not have already, I'm not saying that you should already know how to do this, but hopefully with practice, we're able to do something like that. Like maybe now, if I tell you divisible by 4, you can think of something divisible by 5. Or maybe if we say, hey, I want hexadecimal numbers that are divisible by 3, or octal numbers that are divisible by 3. Saying that would be easy, but hey, we now maybe have an idea of how we can work. All right, you get how the binary works a lot. So when you revise the session, first solve it for the regular decimal, then try to do it for here. I'll tell you for now, like as a trick, if you want, simply do what we did at the end, which is concatenate. Like right now you have a remainder of 2, yes. So it's this. Just concatenate to it what you want. So either 1 or 0. And to that, do the remainder after. Okay. So do the model there. And hopefully you'll be able to see the relation. If you didn't 100% get it, that's okay. If you like maybe 50, 60% you got it, that's good. When you revise, hopefully it'll be even. Okay. If there are no other questions, we can now move to this next slide.
Abba,
Yes, dear.
I have a question.
Please.
In the book I saw exercises about concatenation. مثلا بيكون عندي a language that accepts something and something else يعني بيكون في كلمة and.
What do you mean?
Okay. Like لحظة let me tell
So
you.
like what we did here at the start, like I have language L prime
No.
concatenated with L1.
No, I don't think so. So the question is, we have two languages, such as W has exactly 2 A's
Okay.
and has at least 2 B's, for example.
Okay.
يعني like في كلمة and. Okay.
So that means you have two properties. That's like me saying A is even and it's a multiple of 4.
Yeah,
There's
you
two
will have to you will have to separate them into 2 DFAs and then concatenate them. ما بعرف إذا قاطع عليك هيك سؤال.
You can send it to me. I'll check it later. But that's completely fine. Like there's even a question today, hopefully if we're able to reach it, that I think is similar to what you're trying to say. So if you're talking about like writing it into 2 different machines, I kind of get what you're saying. You're literally in the area of maybe NFAs. It could work for DFAs, but with NFAs we can really understand what you're saying. So to actually reach that, we have to now introduce NFAs. But first, this quick exercise. So hopefully with time, we're going to answer your question, and please do send it. I'll just send right now my email in the chat. You can send me the question there. I'll check it on.
Okay.
But now, draw a DFA that accepts the language the following. So I have some string that belongs to, so this is just all the strings that are made up from A and B. So this is actually a regular expression. You might have already taken it. We'll talk about it in detail next week. But for now, it's just think about it, any strings that are made up of A and B. And W has to end in 2 A's. Okay, so how could I do this? Does anybody maybe have an idea how many states I need here? They're saying I want to end in 2 with 2 A's. So really there's nothing, okay, so I'm just saying maybe 3 states is what we need. That seems about right. Why? I read an A. I read another A. Okay, I have 2 A's, or at least I know that I am 2 A's, which is good. But how now I have to fill everything else. So yes, I need only 3 states, but how can I fill everything else? So for example, here, if I read an A, where should I go to? Yeah, I just loop over myself because if I end in 2 A's or 3 A's or 100 A's, it doesn't matter as long as I've already confirmed that at least there are 2 A's. If there's more, that's great. More the merrier in this case. But what about if I, so actually if you look at the graph, we're done with the 8 transitions for the entire graph. All that's really left is the transitions. So where does the B take me in these states? Go to the beginning. Yeah, for all of them. If I'm here and I read a B, it's like it resets my counter for the A. If I'm here and I read a B, I also go to the start. Like I have to now check again if I'm reading 2A's. And if I'm here at the start, that's fine. I just do at myself. But I need to have DFA rules for every symbol in my alphabet. I have to have a transition coming out. It could go back and with a loop, that's okay. That's it. All right. Now, if you remember from last time, these were not allowed in DFA, but now they actually are allowed in NFAs. So how would that look like? So you are allowed to have a single, not all the transitions coming out, like in the first one. You're allowed to have more than one transition for one, like in the second one. And finally, you can have the epsilon transitions, which we'll explain in a second. Now, all this first one means is, let's explain each one. All this really means, if I'm at this state and I read a 0, it's as if you're saying reject. So right, say you're parsing your string and you reach this state. I don't have, so I call it Q0. I don't have a 0 coming out, so you just reject. It's as if there's an imaginary transition that takes you to the rejected state. For the second one, it's pretty self-explanatory. If I'm currently at Q1 and I read a 1, I have 2 paths. I can either go here or I can go here. If I'm at Q2 and I read this, this is what we call a free transition. So like say your string is 0, 1, 1, 0. Say you're parsing the string and you're currently here and I reach Q2. Now technically, so let's say Q2 goes to Q. Technically, I want to read the 0. But since I have this epsilon transition, it's like a free trip. I can go from Q2 to Q3, now I'm Q3, and I didn't have to read this 0. So I stay where I am at the parsing, but now I reach state Q3. And now from Q3, depending on what I have, I go somewhere. That's the rules for NFA that are allotted. Knowing this information, how can we now do the same problem but using NFAs? It's the structure of it is going to stay the same. Like I'm still going to be wanting to read an A here and an A here. The structure is the same. Oh, and I think we forgot back when we did it with the DFA, we simply forgot to make this one next time. So the base structure I still need to read 2A's, but what about all of the other transitions? Andre, what I don't understand is how is it possible to implement such a machine physically? Yeah. Well, for now, remember that we want to have a question in the back of our mind, a really big question, which is what is a computer? There's the physical sense, and now what we're talking about with these basic machines is the abstract sense. So for like this is the building block that what actually led to the actual physical computer. So hopefully we'll be able to answer that question in the coming weeks. But for now, the only thing we can answer, what can I do with the rest of the transitions? So imagine you have this string which is a bunch of A's and B's. All you really care about is the AA, which is what I have here. This is technically a valid NFA. This is a valid NFA. What does the language that this NFA accepts? It accepts the language that has the string A. This is all that it currently accepts. If you give it AA, it will accept it. If you give it anything else, it will reject it. How can I modify it using the rules of the NFA to accept it? Any idea? Oh, epsilon to the beginning. From where? From the beginning to the end, like this. Now, I could technically do this. This is still an NFA, but now if I do this, I will now actually also accept the empty string, which isn't really what I want. I want my string to end in 2 A's. I can do this, still an NFA, but it's now not, I accept a string that I shouldn't accept. So it's like a false positive. You're accepting something that you shouldn't. And I don't need epsilon just to. There's going to be an exercise on epsilons today. I don't need that. So all you really need is these two rules. So either this one or this one. I can either have a state with one transition or I can make multiple transitions instantly.
So we can make a B transition that takes us to the same state
We could do that.
every time.
Where do you want to do that?
What?
Yes, you can do that, but where do you want to do that? So you're saying you want to make a state loop on itself on B, yes? Where do you want it?
On the states, I think. No, it's fine.
Okay, let's see. If I can, so you're saying all the states, but same as before, I can now accept the string A, B. Why? I read an A. I read an A, then here I read a B, and I accept it. So again, I'm accepting things that I don't want.
So we can make like the B take us to a trap state every time.
Why? No need, right? Remember, NFAs helps us facilitate that. If you don't have the transition, you'll go to a trap yourself. What I'll tell you, Mariam, this is what you only want the B loop here. You don't need it for the rest. Now, there are multiple solutions with NFA. There's no one unique solution. But I'm telling you, only having a B transition here is more than enough. And I want also an A transition. And this is the solution. Why? Why does this work? First of all, it's an NFA, of course, because some states don't have all the transition, and some states have more than one. Like this first one, Q0, you'll notice I have an A coming back to me looping, and I have an A going to say Q1. So why is this enough? In NFA, we have something called multiple runs, which I'll explain in a second. But think about it like this. Since you have a loop going back to yourself at the start of A to B, it's as if you're reading all the A's and B's at the beginning. Like you don't care. You're quickly going over all of them. Then you're checking, hey, do I end in A? This is what this NFA is doing. This first loop at Q0AB, I'm quickly exhausting all the unnecessary A's and B's. Then I check, hey, do I have an A and I have another A? It ends like that. Great, I accept. Andre saying something really good. Is it because we only need one of the branches to succeed? Exactly. We'll say what the branch is in a moment, but yeah, I only need one of them to succeed. Let's explain the difference between DFAs and NFAs, and it'll make what I just said more clear. So in DFAs, it's called deterministic, which means I only have one run. So if I actually go and grab the DFA that we did. There's only one possible one. What do I mean by that? Let me first just name the states. So this is Q0, Q1, and Q2. Say we have A, B, A. No matter how many times you parse this string to do this DFA, it's always going to take the same route. I start off at Q0. I read an A, I go to Q1. So I'm here. I read an A, I go to Q2. Here. I read B, I have to go back and reset at Q0. Then I read two more A's and I go to Q1, then back to Q2, and I accept. No matter how many times you run this, it's always going to go through this route. It's always going to go Q0, 1, 2, 0, 1, 2. That's because it's deterministic. The way we structured it, all the rules that you have to have exactly one transition for each. You can have more than one transition, etc. All these rules give us this functionality, which is deterministic, only one run. But if I go and now do the same thing for what we did here, with non-deterministic, which, as Andre mentioned, it has multiple runs, it has branches. What happens when I try to do the same string here? A, B, A. Okay, I'll start off and say Q0. Right away, from the get-go, at Q0, two possibilities. Do I stay where I am or do I go to Q1? So if I did an A, I could stay where I am, or I could go to Q1. If I continue from here, so at Q0, so far I've read 1A. Again, stay where I am, or I can go to Q1. Now, if you actually focus here on Q1, so far it's read two A's. A. So I'm currently at Q1, and I'm trying to read a B. I don't have the B transition coming out of Q1. So this branch is like that. It's rejected. This branch doesn't work. But be careful. It's not the string that's rejected. It's only this run where I read an A, and I ended up at Q1. This road doesn't work. But the cool thing about NFA, we only need one road to work. We only need one branch to be accepted for the whole thing to be accepted. If a lot of them are rejected, if all of them are rejected, but only one is accepted, that's okay. I'll accept. At the NFA, we'll accept the string. Now, if we keep going here, at Q0, I can only go from here to myself. I don't have any other branch, so I have to do that on myself. Then, again, I can either stay where I am, or I can go to Q1. Now, this road, if you keep going, it's gonna also be rejected. But if I continue here, so far I've read A, B, A. I can read again one more A and go to Q2. It gets excellent. So this is, so the whole thing gets accepted, and this is the idea of multiple runs, multiple branches, is if one is okay, then the whole thing is okay. And again, you might have multiple accepting branches. That's great, but just one is. Okay. Now we're out of time, just need a couple of more minutes. So, which language is actually stronger? So both of these accepted the same language, but which one is actually better? Well,
NFAs.
So the NFA definitely feels like it's stronger because it's giving us more freedom. I don't have to put all the rules. But is it really strong? Well, first of all, what does it mean to be stronger? Like if we're talking about physical computers, okay, this has a better CPU or this has more RAMs, so it's stronger. But in the abstract sense, what does it mean to be stronger? Well, here we're going to define it as the languages that you can accept. Remember, languages, they're just, for now, family of strings. Is there a family of strings that this NFA can accept, that this DFA can't? If yes, that means it's better than it. Is there something like that? Well, to answer it, we need A power n, B power. So what's this? Essentially, so A and Bn, it's the family of the strings that are in this formula. So we have the empty string. So it's an equal number of A's followed by an equal number of B's. So you could have the empty string, or we sometimes say the epsilon is the empty string. I could have 1A, 1B. I want to keep writing the quotations. I could have 2A's, 2B's, etc. It has to first start with the A's, end with the B's, and they have to be the same, etc. It's infinite. I could have 100 A's followed by 100 B's. The important thing is that they're the same number. However, no matter how much we try, we can't do a DFA for this. Why? Everything we've been doing so far with the DFA is kind of like tricking, like, oh, I have states. I'm giving the illusion that I have memory when I say even B, even odd A, etc. But I don't really have memory. I don't have a variable int count that can count how many A's I've read so far or how many B's I've read so far. The best thing I could do with this question here is something like this. Best thing I could do is, well, I'll read some A's, and if I read a B, I'll read B's. Okay, and I'll have both of them accept. What does this language accept? It accepts the language AN, BN, such that n is bigger than or equal to 0, and m is bigger than or equal to m is bigger than or equal to 0. But notice I didn't use the same symbol because I don't have control over that. All I can really control is, okay, you have a sequence of A followed by a sequence of B. But I can't say that they can be the same. Another thing I could do is this. I could say, well, so this is the start here. I could have done something like this where, okay, I read an A, then I read another A, then I can read as many A's as I want. And if I read a B, I start reading like this. Of course, we have to make this a complete DFA, so I have to put all of the transitions. But what this does is the following. It's the language of, I think I'm doing regular expressions without meaning it. It's the same language, AN, BN, such that I have at least 2 A's followed by as many B's as I want. Like I can have control maybe on the lower bound, but not on the actual 2 variables. And if you try to do the same thing for NFA, you're going to run the same problem. Really, all that NFA did was this. It allowed you to use these tools, which gave you more freedom, definitely. But I don't see a variable. I don't see a way where I can get more. So we'll run into the same issues where the best thing you could do is a certain thing. Like I could do maybe this. And put an epsilon in here transition. It's like a free transition, and I read these. So this is L1, this is L2. I just did L1 again. So to me, it seems they accepted the same the same languages. Like this A and B N, it's a ceiling to both of them. There's a language that we can't do using these machines. So we're going to be learning later stronger machines that will be able to do this language. But for now, we can't touch this. Ronnie's saying NFA is computationally less complex. It feels easier to do an NFA. Like it seems like I can write less transitions. Sometimes I can do less states. So there's more freedom there. Yeah. And actually, if you think about it, so this is an important, every DFA is an NFA. Why is that? Every DFA is an NFA. Because before, with those new rules, we simply said you are allowed to use them. You're not forced to use them, you are allowed. So if you decide not to do them, like if you put all the transitions in exactly one, you make a DFA, that's still technically an NFA. However, not every NFA is a DFA. So the opposite direction doesn't work. Simply because the things that are allowed in NFA are not allowed in DFA. But that doesn't mean that one is stronger. If we define strength as in what languages they accept. They can, if you can do something using an NFA, you can also do it using a DFA. So what you do here can be done. Since every DFA is already an NFA, of course, like if you do a DFA, you already just did an NFA. Andre, can we say that every NFA has an equivalent DFA? Definitely. There's even a rule. There's an algorithm that you follow which transitions, which changes an NFA to a DFA. So there's an algorithm that, hey, given an NFA, you can change it. You make more states and you can come up with an NFA. And we might do that next time. But for now, I'm gonna end it here. I'll leave you just with this question for you to read and try to solve this problem. I'll send in the link again. I'll send in the chat the links that you can use to draw something and the links that you can submit. So you can either submit here or just send it by email. So try to solve this. I'll try to add your solution to the slides when I post them and put some marks, or maybe I'll do a video on your submissions. Let's just read the question and we'll stop. Give an NFA for the set of all binary strings. So binary strings just means they're made up of zeros and ones that have either the number of zeros, multiple of 3, or number of ones not a multiple of 3, or both. So really both means like both conditions could be true at the same time. That's okay. So like both isn't really a third condition. It just means you have more accepting states. Doesn't necessarily mean you have states, just more accepting. Okay. Now, when you try to solve this, I want you to think in an NFH format. Like I know we could do this using a DFA. Just a question, can anybody maybe guess how many states it would take to do this using DFA? If I want to do this the old-fashioned way with just DFA, like using the old questions, how many states I have. Well, for the blue condition, there are 3 possibilities. Either the 0 is divisible by 3, like the number of zeros. By the way, this isn't a binary number where you actually have to check if the number is divisible by 3. It's just the number of zeros. So there are 3 possibilities. Is it divisible? If it's not, remainder 1 or 2. Same thing for the 1. So you can actually do this using 9 states. If we're talking about with DFA. Not sure if there's less, but like the straightforward solution is you can do it using 9 states. I'll give you a hint. With NFA, you can actually do it in 6 states. But it's actually 7 with starter, or yeah, the starters. I don't want to call it something else. That might be too much of it. Okay. And again, both just means you have another example. So, like if you only have the blue condition, you accept. If you only have the orange, if you have both of them, this you have also. So try to solve this. You can send it my email, and I'll check your answer check. If you have
Do
any
you have
questions,
office hours?
just for now, it's by appointment. Like if you ever need to meet, send me an email. We can schedule a time that fits us.
Okay.
Andre, in NFA, are you allowed to have multiple starter states? That's a weird question. Actually, I'm not sure if like I'll check that for last time. So what you're asking is, can I have like in general, can I have a DFA or an NFA where I say this is a start and this is a start? I'm not sure. Because if you actually check maybe the definition of what an NFA is or a DFA is, like the actual mathematical definition, it might say you only have one starting state. If it says you can have a set of starting states, just like you have a set of accepting states, like I have Q1, Q2 could be my accepting. If in the definition it says that, like you can have also multiple startings, then yes. If not, then you only have one. But just to answer your question, Andre, in case not, in case I can only have one starting state, you can do a trick where you can have multiple. Yes, like you're saying, you need 2 starting, right? You need say start 1 and start 2. Simply just make an actual start 0, where if you get an epsilon, you go to this state, and if you get an epsilon, you lead to this state. And then there's no need for this or this. So that's like if you have like if you feel like you need 100 starting states, just make one as 0 that actually. That's again the neat thing with. So we could not have done this with DFA. Okay. There are no more other questions. So in the period, and then please really hoping that I can see you. I'll see you next time. Yep.